Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video here is to just go through an example of how to analyze a projectile problem. And the problem we're going to look at here is modeled after the Pirates of the Caribbean. If you've seen the movie Curse of the Black Pearl here, and there was a scene in the movie when the pirates were trying to come to shore here. So what we have right here is we've got the Black Pearl. And we've got little Timmy here playing basketball that sees that ship coming. And Timmy's going to try to defend the port here with his cannon, which has a known muzzle velocity of 800 meters per second. So the big question here is Timmy needs to know at what angle with respect to the horizontal he needs to point that cannon to have a shot at taking out the Black Pearl at a 1500 meter distance. So some things about this problem to consider before we get rolling here. First, this little height difference really is not significant in the problem, so we're going to assume that the cannon and the ship are basically at the same level. Second, we're going to be assuming that cannon has a known speed of about 800 meters per second. Third, we're going to assume that air drag is negligible for this problem. Now, at 800 meters per second and a cannonball, especially 1500 meters out, that may not be a 100% valid assumption, but again, the point of this video is how to work a projectile problem. We're going to just try to get an approximate angle for theta and not worry about air drag. So, the first thing we need to do in a projectile problem is we've got to consider the initial velocity vector. So the cannonball is going to leave that cannon, and its initial velocity vector is going to be kind of up and to the right. Now, in this example, the magnitude of that velocity vector is 800 meters per second. When you're working projectile problems, typically what we do is we analyze the x and y motion independently. So in order to do that, what we need to do is we need to take that velocity vector and we need to break it down into its horizontal and vertical components. So if I draw them in this picture, that one I would call initial velocity x direction, and then right here initial velocity y direction. And then this angle, this interior angle, would be the angle theta that we're trying to find. Now, this being a right triangle, we can find these components by right angle trig. The v sub o x here is adjacent to the angle theta, so it's equal to v sub o cosine theta. The v sub o y is opposite the angle theta, so it's equal to v sub o sine theta. Now, if you want to put 800 meters per second cosine theta, 800 meters per second sine theta, that's perfectly fine. I'm going to go ahead and work this problem out algebraically. It's just shorter to write v sub o, and it's just better mathematical form to leave these in variable form as far along as you can in these problems. Next, all right, velocity and acceleration and position. These are all examples of vector quantities, and when you're dealing with vectors, you need to have a coordinate system in the problem. So I'm going to go ahead and put my coordinate system here. Now, exactly where, not that important. I'm going to put my coordinate system, oops, not blue. Let's use green for our coordinate system. It's a nice, happy color. So there's going to be my x-axis, and then this is going to be my y-axis. Now, the reason I'm putting it at the foot here of the cannon is just basically room here. I don't have a lot of room on my page. Basically what I mean by this, oops, the coordinate system origin is basically where the cannonball is being fired from. This little 5 or 6 foot difference here is not significant over the 1500 meters away that this ship is. I just didn't quite have enough room, I didn't think, to put the coordinate system right there. But basically what I mean by this is the cannonball starting at a coordinate of 0, 0. Now, all right, so x-axis, y-axis. Now we'll start analyzing the motion, and if you've got me for physics, you know that I love graphs. So I'm a big believer in using graphs to analyze the motion of a particle. So I'm going to start by drawing a velocity graph. And next I'll draw a position graph. Key concept here, though, is that what we're going to do is we're going to look at the x motion, or the x direction first, and we'll do the y direction second. So velocity in the x direction against time. This cannonball, as it flies through the air, the acceleration direction is down. It's accelerating vertically because of gravity, and we sometimes call that the gravitational acceleration. And a key assumption here is that there's no acceleration horizontally, which means this velocity vector is going to stay constant. So in this graph, this is going to be horizontal out to some time t. And the value here is equal to v sub o cosine theta. Now our position graph, right, when we draw this guy, when we talk about position here, we're talking about the x coordinate here, because remember we're doing this one coordinate at a time. So now I'm going to draw a graph of x against t. And when your velocity is constant, that means your position is going to be linear. And again, remember that velocity is the slope of position. It's the rate that your position changes. So the velocity is the slope of a position graph. And if your velocity is constant, that means the slope is constant, which is going to give you a linear function. Now, as far as the equation that describes this, there's a couple ways to get it. I'm going to start with this. Your change in position, or your displacement, is given by the area bound within your velocity curve. If you're not familiar with this, you can go back and look through my video set here, and I've got one that talks about finding the displacement using a velocity curve. So this area right here gives the delta x. And that area is equal to, let's see, this dimension is v sub o cosine theta. And then this dimension is t. Now, it's important to realize that this area gives you the displacement, the change in x, which is equal to x final minus x initial. X initial is basically 0. I say basically, I know the coordinate system origin isn't exactly here, and that's just because I was kind of running out of room. But over a 1,500 meter distance, basically the cannonball is starting at 0, 0. So now we have x equals v sub o cosine theta t. So there's the function that describes this line. Now, keep in mind I'm working this thing out algebraically. The v sub o is a known value. The x is a known value. However, theta and t are both unknown. So now we need to move on. Now we're going to take a look at the y direction. So as far as the y direction is concerned, this cannonball is accelerating. It's accelerating down at about 9.8 meter per second squared, which I'm just going to call g. Right? Acceleration of gravity, approximately 9.8 meter per second squared downward. So when we draw our velocity graph for the y direction, against time, taking note of the fact that this is a constant acceleration problem if we ignore air drag. Then here's what this graph is going to look like. Right? Our velocity y direction at t equals 0, the cannonball does have a velocity in the y direction. In our original picture, that's here. Initial velocity y direction is up, and its magnitude is going to be v sub o sine theta. Now, we don't have a number right now because we don't have the theta part, but we do know that it's up, so this is going to be some positive value. So I'm going to go ahead and put that value maybe here. Now, because the velocity is decreasing, because of the gravitational acceleration, this graph is going to look something like this. It's going to be linear. If you don't mind, I'm going to go back and redraw that. And it's going to have negative slope. Now, the reason it's linear, because the acceleration of gravity is not changing. This thing is not going to reach a height that's high enough to drop that acceleration. Right, the acceleration of gravity pretty well everywhere on the surface of the Earth is around 9.8 to two significant figures, about everywhere you go, meter per second squared. Because the acceleration's down and I've got up positive, this graph will have negative slope. Numerically, what we're saying is that for gravitational acceleration, we're going to use negative 9.8 meter per second squared. And again, the minus sign is because I've got up positive, but the acceleration is downward. Now, next, we want the equation for this line. This is going to be v equals v sub y equals something. Now, there's a couple ways to get that equation. I'm going to go ahead and do this. Acceleration is equal to change in velocity over change in time. So your change in velocity is equal to acceleration times your change in time. Your change in velocity is equal to v final minus v initial. Now the initial velocity in the y direction on our graph, that's this distance, and I haven't labeled it yet. In this picture, that's this vector represented by v sub o sine theta. So our change in v is going to be whatever v final is minus this. So that's what our delta v would be. The acceleration, I'm going to go ahead and write that as minus g. The minus because it's down, and then g has a numerical value now of 9.8 meter per second squared. And then our delta t is going to be t final minus t initial, which I'm just going to call t minus 0. If we start our clock here at t equals 0, our initial time would be 0. This is our final time. If you solve this equation for v, you get v sub o sine theta minus gt. Now, there's the linear function that describes this curve. Oops. Next, I'm going to sketch y coordinate against time and talk about how to find that equation for that. Okay, so we're going to look at y against t. Now, first thing to take note of is at t equals 0, the cannonball is basically at our coordinate system origin. Again, this little difference here is not important over a problem over a 1,500 meter distance. So I'm going to put the first point right here. And then sometime later, I noticed that the cannonball, as we kind of think about its flight through this problem, sometime later it's going to be quite a ways off the water. Now, how high, I don't need to know that right now, but suffice to say that this is some positive value. And then it's going to come back down, and eventually it's either going to drop short, hit the ship, that's what Timmy's hoping for, or maybe we're going to fire too far. This curve is going to look something like this. It's important to realize now the relationship between these two. Our velocity curve, again, remember this is velocity y direction, where this is 0, that means the slope of the tangent line for our position graph would be 0. So this point on the graph corresponds to this point right here. I'm going to go ahead and redraw that curve. I'm going to put a dot up here where the tangent line has 0 slope. So this is looking something maybe like this. Now, as far as finding the equation for this curve, there's a couple different ways. And again, if you're in a calculus, if you're familiar with differential and integral calculus, you can use that. You can use the fact that this velocity is equal to dy dt and use an integral process to find this function. I'm going to go ahead and do this a little bit more generically and just use concepts of area to find this. So what I'm going to do here is I'm going to go back to my velocity curve. And I'm just going to pick a point on that curve. Now this is a generic point. You can think of this anywhere. This coordinate is t, and then This distance is the velocity that goes with that time. That's described by this equation. Your change in position, in this case your delta y, is given by the area bound under your velocity curve, or I should probably say within your velocity curve. In this problem, I'm going to draw this in red, that's this area right here. Now the reason for picking kind of a generic time here, you don't want to put your point here because then your equation would only be good really at that time. I'm picking kind of a point on this curve, I'm leaving it kind of generic so that my equations are good everywhere within the problem, the entire time this cannonball is in flight. This area would give the change in position for any time t. You'll notice that this is a trapezoid area, and if you've seen my videos on how I typically handle these, what I usually do is I go right in the middle, draw myself a rectangle. Whoops. Take note that this rectangle has exactly the same area as the trapezoid. I could cut that off, that triangle, glue it right there. Has exactly the same area. The reason for doing that, well, a rectangle is a very easy geometry to deal with. The area is just length times width. So this dimension is t, that's no problem. The only kicker is you got to figure out this height right here. Now, I always think of Goldilocks and the Three Bears here. This height is less than this distance, but more than this distance, and it's halfway between them. It's the average of the two. So this distance is v sub o sine theta. This distance is described by this function, v sub o sine theta minus gt. So this height is the average of the two. So that's going to be, if I write it out, v sub o sine theta plus this distance, v sub o sine theta t. Whoops, I'm going to need more room here. I'm going to back up and redo this. Back what I'm going to do. So I'm going to take this whole thing here. Just bear with me, anybody watching this video. I just need more room to write. Oops. Try this again. Need to create more room here. So what I'm going to do here is just take this whole thing and move it to the left. Okay. So now again, this area is this distance, which is t, times this distance, which is the average of v sub o sine theta, and this velocity defined by this curve. So that's going to be v sub o sine theta plus v sub o sine theta minus gt over 2. Again, that's the average of this distance and this distance on this graph, and then times this distance, t. So what we get out of this is delta y, our change in position, is equal to, by the time you simplify this a little bit, you get v sub o sine theta t minus, and then 1/2 gt squared. Now I'm just going to take note of that this delta y is y final minus y initial, and y initial is 0. So really this delta y we can write as just y. So I think what I'll do is I'll just go back instead of recopying it, and I can just replace that delta now. So there's my function for y against t. Now basically all projectiles can be analyzed like this. We've got an equation now for x against t. We've got an equation for y against t. The next thing to do is basically just glance these over here. So we know an x, we know a v sub o, but we don't know a theta, we don't know a t. Looking over here now, if the cannonball scores a hit, basically its y coordinate is 0. The v sub o is known, the sine theta known, not known, and the t is not known. So what we have here is two equations, two unknowns. We don't know t, we don't know theta, we don't know t, we don't know theta. So the next step in this problem is an algebra step. I'm going to go ahead and get rid of, I'll some of the work I don't need. Oops. Just for the sake of room here. I don't need this stuff anymore. Now we'll just work on the algebra here after I clean this up just a little bit more. All right, so now we're working with these two equations here, and what I'm going to do is eliminate time from them. If I solve this one for t, it's equal to x over v sub o cosine theta. So now anywhere we see a t, we can put that value, x over v sub o cosine theta. What I'm going to do is rewrite this equation now, subbing this in for t. So what we're going to have is y equals v sub o sine theta, that's this term right here, times t, which we know to be x over v sub o cosine theta from this equation, minus 1/2 g t squared. And again, the t can be written x over v sub o cosine theta. And again, that's being squared. So what we got now is we've got this fairly long-winded equation here, but it doesn't have time in it. This equation now has only one unknown within this problem. The unknown is theta. So what I'm going to do here in this example, I'm going to go ahead and write this equation out. At this point, I'm just going to put numerical values everywhere where I have them. So basically, if Timmy gets a hit, the y coordinate is 0. Now you'll notice the v sub o's here cancel. X is 1,500 meters, and I'm going to write this without the units because I don't have a lot of room, so I'm just going to put NCU for note consistent units. So there's my x, the v sub o's cancel, and then what we have here is tan theta minus, okay, numerically now, the g is known, the x is known, the v sub o is known, so what I'm going to do is just put those values in. 1/2, g is 9.8 meter per second squared. Now this term right here, x over v sub o, is going to be 1,500 over, oops, let me write that 1,500 a little better, 1,500 over v sub o, which is 800. And don't forget that that quantity is being squared, x squared, v sub o squared. And then we're going to have times 1 over cosine theta. And that cosine theta, again, is being squared because of this term right here. So we've got kind of a long-winded equation here. I think what I'm going to do here is I'm going to just stop or pause the video for a moment while I clean this up a little bit and get numerical values. So bear with me. I'm back here and we've got this cleaned up just a little bit here. I had one of my helpers here give me a value here. So this quantity right here ends up being 17.23. Now we still got a reasonable equation here to solve for theta. This is a cosine squared, and keep in mind that tangent is sine over cosine. So the next thing to do is clear out the fractions by multiplying both sides by cosine squared. So left-hand side, 0 times cosine squared is still 0. Sine over cosine times cosine squared is now sine theta cosine theta. And then this term, the cosine squareds would cancel, so we'd be left with just 17.23. All right, next move. If we put this on the left and divide by 1,500, the next line is going to read sine theta cosine theta equals, would somebody give me 17.23 over 1,500? .0115? Is that right before I move on? I don't hear you. I don't hear real well. Yep, okay, looks good. Okay, so now got to work on the solution of this equation. If this were sine theta equals 0.0115, it's just a matter of taking the inverse sine of both sides. Same thing with the cosine, right? But it's not. It's the product of the two. So what we need to do is this needs to be simplified down via some trig theorems here. And one of the theorems of trigonometry, and I'm not going to go through and prove this one right now, but one of those theorems of trigonometry is this. 2 sine theta cosine theta is equal to sine of 2 theta. I'm going to take a moment here. I just want to double check that. I'm going to pause this because my memory is like a bucket with a hole in it. I'm just going to triple check that that's correct. If I got back after verifying that, I just wanted to go through that one more time because, again, my memory is not as good as a lot of people's. So what we can do here is use this trig theorem to simplify this thing down. So what I'm going to do is multiply both sides by 2. Actually, I need some more room here. I'm just going to get rid of all of this stuff here. Oh, no, I'm not. I'll just get rid of this. Okay. And again, I'm going to take this guy and just move this up where we can work on it. All right, so again, multiplying both sides by 2, this is now going to read 2 sine theta cosine theta equals, this is now going to be 0.0, yeah, whoops, 0.0231, 0.023, yeah, that looks right. All right, next step is divide both sides by 2, so now we're going to, whoops, no, next step is that 2 sine theta cosine theta is equal to the sine of 2 theta. Next step is to take the inverse sine of both sides. Would somebody please make sure your calculator's in degree mode and give me the inverse sine of 0.023? .32, okay. Now, when we take the inverse sine of both sides, was that 1.32? Yeah, we get 1.32 degrees, but keep in mind the inverse sine of the left-hand side is not theta. If you take the inverse sine of the sine of 2 theta, what you get is 2 theta. Now I'm going to come back and talk a little bit more about trigonometry here in just a moment. I'm just going to keep going and solve this. So the last step here is just divide this by 2. So theta equals 1.32 divided by 2, which is, what does that come out to be? What's it come to? 0.6? Okay, approximately 0.66 degrees. So it looks like a fairly shallow angle there. I may go back and take a look and make sure these numbers are all right, but again, 800 meters per second is a fairly fast, it's a reasonable muzzle velocity. Now, I'll go back and talk about this guy right here. When we take the inverse sine of both sides, your calculator will always give you an angle between minus 90 degrees and plus 90 degrees. That's because the inverse sine function is only defined in that region. However, this equation here actually has 2 valid solutions to it. One of them is in quadrant 1, 0 to 90, but the other one is a quadrant 2 solution. If we take 180 degrees minus 1.32 degrees, we get 176.8. Is that right? So another solution to this equation is 2 theta could equal 176.8 degrees because this is a second angle that has a sine equal to 0.023. It's a quadrant 2 angle. And then if we divide that by 2, now we get, what's 176.8 divided by 2 there? 88.4 degrees, right? 88.4 degrees. So there's 2 angles here that Timmy, in theory, could point to that cannon at and potentially get a hit on the zombie pirates here. And this is very common for most projectile problems. If you just think in general how projectiles work, if I did kind of a quick picture, if I have something I'm throwing at some sort of velocity and I have a target, there's, if the angle's too shallow, it's going to hit short. Increase the angle, it hits a little bit less short. Eventually there's going to be an angle that's going to get you a hit. If you increase theta further, you'll overshoot. Increase theta further, you'll way overshoot. But as theta increases, eventually these will come back down, or come back, the impact points will come further, closer to where you're launching it from, and eventually there's going to be another angle that will get you a hit. So as a rule of thumb, projectile problems will have two angles that could conceivably hit a target, with the exception of the very furthest distance this thing can be fired. So anyway, the point of this video is just to go through and give an example of how to analyze a projectile motion problem. I think this video got a little on the long side, but what can I say? These things take a little bit of work. I hope this video helped demonstrate how to do that. Have a great day.